Have you ever just looked at a 400-ton aircraft and wondered how on earth we can predict its every move with just math? Well, the truth is, the equations that perfectly describe flight are, frankly, monstrous. But for over a century, engineers have had this elegant secret weapon to tame them. Let's take a quick look at what they're really up against. So, meet the monster. I mean, just look at this thing. This right here is just one of the equations for the rotational forces on a plane. It's this non-linear nightmare, full of terms that are all tangled up together. Trying to solve this thing directly, it's an incredibly difficult task, to say the least. And believe it or not, that's not even the whole picture. To fully describe how a plane moves, you actually need a set of 6 of these equations, and every single one is just as complicated as the last. You've got 3 for forces, up and down, forward and back, side to side, and then 3 for all the rotations. Which, brings us to a really practical question. If this is what you have to start with, how does any engineer design a plane that's stable and controllable without just getting completely lost in a sea of impossible calculations? There's gotta be a better way, right? And of course, there is. It's this powerful and honestly, surprisingly intuitive technique. It's the engineer's secret weapon for turning these mathematical monsters into something you can actually work with. That weapon is called linearization, and the whole idea here is to approximate a really complex, curvy reality with a simple, straight-line model. You're basically getting rid of those tricky nonlinear terms. It's a mathematical lifesaver, and engineers have been using it for over 100 years to make the impossible, well, possible. Okay, so how does it actually work? It really just boils down to 2 fundamental tricks of the trade that are, you'll see, surprisingly simple. So the 2 main tools in our linearization toolkit are what we call the small angle approximation and then the fine art of ignoring negligibly small terms. Let's break down each one. First up, small angles. See, for most of a plane's normal flight, the angles we're talking about are tiny, usually less than 10 degrees. And when an angle, let's call it theta, is that small, the trigonometry gets beautifully simple. The sine of theta becomes, well, basically just theta itself. And the cosine of theta, it's pretty much just 1. This trick is amazing. It lets us swap out complicated trig functions for simple numbers and variables. All right, our second technique is all about knowing what you can throw away. So imagine you have some number a, and you add a really tiny number to it, epsilon. When you square that whole thing, you get this epsilon squared term at the end. Now, if epsilon is small, say 0.1, then epsilon squared is 0.01. If epsilon is 0.01, its square is 0.0001. That number gets so vanishingly small so fast that you can just drop it and it has almost no effect on your final answer. It's a super powerful way to simplify things. Okay, theory is great, but let's see how this stuff actually works in the real world. We're going to take these tools and apply them to a really common scenario, an airplane in a nice, steady, gentle climb. Now, the key word here is steady. Steady flight means no acceleration. And if there's no acceleration, Isaac Newton tells us that all the forces acting on that plane have to be perfectly balanced. They all add up to 0. And that's our starting point. So first, let's look at the forces that are perpendicular to the direction the plane is flying. For all those forces to balance out, the lift from the wings has to equal the component of the plane's weight acting in that same direction. And that gives us this equation, where that little gamma symbol is the flight path angle. Okay, time to use our new tool. In a gentle climb, that angle, gamma, is super small. And what did we just learn about the cosine of a small angle? It's basically 1. So just like that, poof, the complicated trig function vanishes, and the whole equation simplifies down to that famous rule of thumb we all know. Lift is approximately equal to weight. So far, so good. But now things get a little more interesting. Let's look at the forces that are acting along the flight path. This is where the real art of approximation comes into play. So along the flight path, you have the engine's thrust pushing the plane forward, and that has to balance out 2 things. The drag pulling it back, plus a little component of the plane's own weight that's also trying to pull it backward, down the slope of the climb. That gives us our second equation right here. Let's use our small angle trick again. Since gamma is small, the sine of gamma is pretty much just gamma itself. So our equation now becomes thrust is approximately equal to drag plus weight times gamma. And here is the absolute crucial point of this whole thing. We know gamma is a small number, maybe something like 0.1. So that weight times gamma term is just a fraction of the plane's total weight. It seems small. So isn't it tempting to just ignore it? To simplify this even more and just say thrust equals drag, this is the single most important lesson in linearization. The question is never, is this term small? The right question is always, is this term small compared to what? In our equation, we can't just look at weight times gamma in a vacuum. We have to compare it to the other thing it's being added to, drag. Okay, let's break this down. A typical airplane is really efficient. Its lift-to-drag ratio is often 10, 15, maybe even 20 to 1. And we already know that lift is pretty much equal to weight. So that means the plane's weight is 10 to 20 times bigger than its drag. So think about it. When you take that massive weight and multiply it by a small number like gamma, maybe 0.1, the result is still a pretty big number, a number that is very much in the same ballpark as drag. It is not negligible, not at all. The lecturer whose material this is all based on had this fantastic analogy for it. He said ignoring the weight times gamma term next to drag is like comparing your height to another person's height. They're on the same scale, the same order of magnitude. You can't just ignore the other person. But ignoring one of those tiny epsilon squared terms from before, that's like comparing your height to a mouse's. In that comparison, yeah, the mouse's height is pretty much trivial. So what's the big takeaway from all this? It's that linearization isn't just about blindly chopping terms out of equations. It's a skillful art. It's something that requires you to really understand the physics of what's going on. And this leads us to our final correct approximation for a climbing aircraft. We can definitely simplify sine of gamma to just gamma. That's a good approximation. But we absolutely cannot get rid of that weight times gamma term. It might look small on its own, but in the context of the other forces at play, it is not trivial at all. So, to wrap up, the key here is that linearization is a tool for smart simplification, not blind simplification. The most important question you can possibly ask yourself is small compared to what? And finally, context is everything. That old rule of thumb that thrust equals drag, it's perfectly true, but only for the very specific case of level flight where that climb angle, gamma, is 0. It really gets you thinking, doesn't it? If a detail that seems as small as a gentle climb angle has a significant impact on something we understand as well as an airplane, it makes you wonder what other small assumptions in things like finance or medicine or climate models might actually be way more important than we realize. It's a powerful reminder that sometimes the real genius is just knowing which details truly matter.